Laurens, and I'm a second-year PhD student at CWI. And recently I reworked DuckDB's sorting implementation. And I'm going to be walking you through some of the design decisions there that made a lot of difference in performance. So, as you know, sorting is one of the most well-studied problems in computer science. Every bachelor student has to deal with it at some point. And research in this area focuses on things like cache efficiency, like the recent research, and worst case analysis, parallelism, and probably much more. But something this research all has in common is that they focus on arrays, typically arrays of integers, and just this very narrow problem. And while this is great from a theoretical standpoint, in practice, people are not just sorting numbers. They're typically sorting key value pairs, or in case of databases, they're sorting tables. So the use cases of sorting are quite many. So we have just the regular order by clause, but also window functions, sort, merge, join, inequality join, and probably much more. When implementing sorting in a database system, there's a couple of performance challenges compared to just sorting arrays of integers. So there's typically multiple order clauses. These clauses can have different types, strings, whatever the database supports. And analytical database systems usually have a columnar format, and sorting is something that we tend to think about as rows because we're shuffling the rows around, right? So that creates an extra challenge. So to start off, just some terminology. So we're going to distinguish between two column types. So for this example query, we're selecting all of the columns of customer and ordering by birth country and birth year. And we'll call the columns that we're ordering by the key columns. We'll call the rest the payload columns. And of course, to complete the query, we have to order both columns or all of the columns. The cost of sorting in general is dominated by comparing values and moving data. This is in fact pretty much all you're doing while sorting. And moving data is more expensive for relational sorting because of the payload. And in this presentation, though, we're going to be focusing mainly on comparing the key columns, and specifically with a focus on the columnar representation, although some of this will generalize to row store as well. Okay. So as I said, sorting relational data, it's a row-wise operation. So how would we go about implementing this comparison function for columns? Well, it turns out that you need to sort indices rather than the columns directly, like you would for sorting arrays of integers. You can sort the data directly, but here we have to sort indices. And a comparison function could look like this. So the parameter columns are our key columns, and we're comparing two rows. So we have a left-hand side and a right-hand side, and they both have a row ID, and we'd have to loop through the columns. And if columns are equal, we have to compare the next column. If they're not equal, then we're done comparing. Now, this is a simple comparison function, looks good, but there's actually two big problems with it. And that is that because we're sorting indices rather than the data directly, we have to use these indices to look up values in potentially very large columns. And this is basically chasing pointers. Random access, as we know, is slow, and this is not good for our comparison function. This will slow it down significantly. Second problem is that in this comparison loop, we have an if statement, so that creates a branch, and the CPU will try to predict whether it's true or false, and if it doesn't predict well, we'll have a branch mispredict, slowing down execution more. So we'll take a look at both of these problems and what we can do to make it better. So first up, we'll look at the pointer chasing issue. So the solution to the pointer chasing issue is rather than sorting the columnar, like on the columnar data directly, we compact the key columns into a row. And here we still need the ID because we need the ID to reorder the payload after we've ordered the key columns. And by packing the rows into, packing the columns into a row, we can sort the data directly rather than sorting the indices that point to the data. So here we're not chasing pointers anymore. And a nice benefit of this representation is that we also get better locality when we're, so in case column 0 is equal in the left and right hand side, we have to go to column 1. But because these values are co-located, they will already be in cache. So when you have to break a tie between columns. So I've simulated both approaches. So something similar is implemented in DuckDB, but measuring the end-to-end there is yeah, you don't get the details of this specific technique. So I've simulated this specific technique. We'll vary the number of tuples, also the number of key columns, and I've created a data distribution with many ties, which kind of highlights the problem even more. And this is something you also typically see in a database workload. And we'll measure the relative runtime difference. And I've run this on my own laptop, which has an ARM processor. So here are the results. Needs some explanation. So on the x-axis, we increase the row count. The y-axis, we increase the key columns that we're sorting by. And so the value 3 there means that using the row format, we are 3 times faster than using the columnar format. And this timing actually includes the column to row transformation. So transforming to rows and then sorting is can be a lot faster than sorting the columnar data directly. And then in this one case, sorting the rows was slightly slower, and that's when we have only one key column. Okay, so clearly this row format is faster than the column format. Now let's take a look, and it deals with the pointer chasing issue. Now let's take a look at the branch prediction issue. So as we saw, the comparison function has a branch in it, and this might be the only branch, but depending on the implementation, there could be many more branches. So there could be a branch for whether we're sorting ascendingly or descendingly. We might need to check for null values when we're sorting by nulls first or nulls last. And if we have many branches in our comparison function, this will become quite expensive. So how can we deal with this? We'll deal with it with something called key normalization. And the idea here is to encode the keys as a binary string. So here we have our same query again. And in A, we see our table. So let's say that's the customer table. And we have 2 entries, which is birth country, birth year, and it's Netherlands 1992, Germany 1924. And in B, we see how this looks like in memory. So this is the values of the bytes that represent this data in memory. And this is on a big endian machine. And in C, we see the binary string encoding of these rows. And what we've done is we've padded the strings to be equal size. We flipped the bits in the birth country because we're sorting descendingly. And we've flip the endianness of the birth year integer, and we flip the sign bit. And now we can compare both columns with a single call to memcompare in C++, and we've eliminated the branches from this comparison. And also null values and collations can also be encoded in this binary string. So I've run the experiment again. We already established that the row format is better. And now I've compared the normalized keys, so the normalized row data versus the row data that we saw before. And as we can see, we get another speed up. And the normalized keys are up to 3.1 times faster, or up to 40% slower when we only have one key column. And this makes sense, right? Because if we only have one key column, there's no branch in there because we don't have to loop through the columns. So we don't get benefit in that case. And again, the time measured includes the time creating the normalized keys. So as you can see, creating the normalized keys and then sorting is faster than sorting the data directly. So a quick summary about comparing values. Comparing rows eliminates pointer chasing, key normalization eliminates branch predictions, and both optimizations are almost always worth it. So now that we've established how to compare values, we can take a look at our sorting algorithm. So in the previous...
Sorry, Laurens, can I ask a question at this point? Since
of course.
You're in transition. Great. So it seems like the materializing the row first helps with it, but that seems like in part because there's not a lot of filtering happening, right? Like late materialization helps for column stores because you can defer getting the data. Did you guys look at anything with like top K style queries where you have to do sorting and then you're only getting a subset of the records to materialize, and how that would impact that first part of the results?
Right. So for top K, we actually have a different implementation. So for top K, you don't have to sort the whole the whole input. So you don't get the n log n. You can actually do, if you're doing top K, you can use an n log k algorithm. So like you could use a min heap or something of that sort.
Okay. Thanks.
Okay. So moving on to the sorting algorithm. In the previous experiments, I've used a Quicksort implementation, specifically PDQ sort, which is a state-of-the-art Quicksort implementation. And now we'll try to figure out whether this is the right choice for our normalized keys.
The author of PDQ sort is actually also Orson. He's in the comments.
That's me. I literally just joined CWI like a month, 2 months, somewhere in between ago.
Continue, Laurens.
Okay. So our key normalization enables byte by byte Radix sort. So what we can memcomp, we can also do a Radix sort on. So to verify what's better, I've implemented Radix sort, and I've implemented least significant digit and most significant digit Radix sort. And LSD Radix sort's better for a smaller key size, and MSD Radix sort's better for a bigger key size. And it recurses into insertion sort when we have when we have a low bucket size, and this is a very common thing to do with MSD Radix sort. Now we'll take a look at how much a Radix sort can improve over PDQ sort in pretty much the same experiment, same input data. Okay, so it's all red and it's looking pretty bad for Radix sort. So it's at some point it's just as fast as PDQ sort, and in many cases it's much worse. It looks bad, or does it? So there's actually something wrong with the simulation here. So this is not very realistic, and there's a reason why. So in the simulation, we know the key size at compile time. I only have a very specific number of key columns that we're sorting by, and that means that we can compile the comparison function between these, like structs that you can lay over a row format. In practice, we don't know the key size. So we can have any number of order clauses, any number of types, and these can have different widths. So we cannot know the key size at compile time. We cannot pre-compile the comparison function. So how much does PDQ sort, or I think any sorting, comparison-based sorting algorithm benefit from this? Well, the answer is a lot. If we have a parameterized comparison function and we run the same experiment now with a dynamic comparison, then it's looking a lot better for Radix sort. As we expect for smaller key sizes, Radix sort performs better than Quicksort or PDQ sort, and it's actually quite competitive even at larger key sizes. And still, this was quite cumbersome. This will be quite cumbersome to get to work in your database system, because you have to define a lot of structs so you can use the iterator interface to use this sorting function. And I've tried using it without the iterator interface, and then you have to resort to memcopies to copy the data around, and it is a lot slower. So to make Quicksort efficient, there's a few things we can do. So, or actually, it has to do with the struct. So we can create a lot of structs, and template them with comparison functions. And then we can cover a lot of different inputs that we might get to our sort operator. However, this will blow up your binary size. If you template a lot of structs and have a lot of these big switches that create these structs, then the binary size grows by size of hundreds of thousands of structs. This is not something we want to do. So DuckDB wants to be a small portable database system. Other database systems might choose to do this.
If I can interrupt, it's not just binary size. Code cache also matters. If you have a lot of code, that also needs to get loaded in the CPU, and that also actually hurts your performance, not just the actual performance, not just the binary size.
Yeah, and the compilation time, if you care about that, that's also I think. And at this point, it becomes a bit of an arms race, because we could also use these structs to speed up Radix sort, because it's now doing a mem copy, but we could also do assignment if we have the right size structs to copy the data around. And at this point, it kind of becomes an arms race between the cleverness of the implementations, and we don't think that's specifically worth it. So summarizing the sorting algorithm analysis, it's the performance depends on key size and the distribution of the data. Quicksort needs compile time optimization because of the comparison function, and Radix sort is not a comparison-based sorting algorithm, so it doesn't need this optimization. Efficient Quicksort is possible for relational data, and as we talked about, it comes at a cost, large binary size and whatnot. Or if you're a just-in-time compilation system, you can just generate the specific structure you need, and it's basically for free. So for JIT systems, by all means, use Quicksort. So are there any short questions so far?
I mean, I'm not sure if I fully agree with the conclusion, because there's one trick I don't think maybe you haven't tried yet. You can, like before, you serialize the key into a binary format, right? So what you can do is you can pad that with zeros so that you have a few common sizes, like 8 bytes, 16 bytes, 32 bytes, 64 bytes, etc. And then you can instantiate PDQ sort only a couple times, once for 8 times, one for 16 bytes, one for 32 bytes, etc. And then it has a fixed size without creating a whole exponential blow up in instantiations.
Yeah, this is possible, but there's there's one template parameter, which is the comparison size, but there's also an offset. So we encode fixed size prefixes, and in case of strings, we might have longer strings than the prefix, and we would need to template a single struct with both the comparison size and the offset size. So after we've done a tiebreaker of the long strings, then we do a subsort of the tied tuples. So this is something you kind of just have to do. And if you doubly template a struct, even if so we're already padding, so we do a fixed size of multiple of 8. You can instantiate this, but even then we don't want to say, hey, I can't complete this query because you supplied too many order clauses. We never want to say we're sorry. So yeah, that's why we choose for Radix sort. Okay, so moving on. So these tricks have been implemented in DuckDB along with quite a bit more. So we've parallelized the sort, and we've made an external sort, so we can sort more than fits in memory. And we've benchmarked this using TPCDS, so specifically the catalog sales table. This is quite a wide table, has a lot of columns, and we tested at scale factor 10 and scale factor 100. And we're always ordering by the keys CS quantity and CS item. And in our experiment, so here are the results. In our experiment, we increased the number of payload columns. So that if you increase that, the memory footprint goes up, and you need to reorder the payload more. And in the scale factor 10 experiment, the table fits fully in memory. And as you can see, DuckDB is the clear winner there. And at scale factor 100, this table no longer fits in memory. So I've indicated where the table takes up 50% and 100% of the available memory on my laptop. And as you can see, only 2 of the tested systems, so DuckDB and SQLite, are able to complete the benchmark. And that's because the other systems run out of memory. And it's interesting because ClickHouse claims to have an external sorting implementation, but still it crashed on this query. And DuckDB is able to complete the query fast. And there's no clear point at where we have to write intermediate results to disk, even though we have to write a lot to disk. And that's also something to do with the very fast write speed of the SSD on the laptop. So wrapping up, sorting relational data efficiently is challenging. I'd say more challenging than just sorting an array of integers. The performance is impacted by random access and branch predictions, and we want to mitigate these problems because they can impact the performance a lot with the row layout and the normalized keys. And as we saw, there's a trade-off between Radix sort and Quicksort, and for us, the Radix sort is the winner because we want to be small and not template a lot of structs. So yeah, that's it. Thank you all for listening.